Right, so hello everyone. My name is Shireen Chand, and along with my co-speaker, Suvaditya Mukherjee, today we'll be exploring an optimization study that we conducted on 3D generative modeling. In simple words, it's to understand what techniques can we use to reduce the time taken to perform 3D generative modeling. The main metric of our study is time, and the main process that we're going to be studying is from text to 3D. Currently, there are not many direct text to 3D models available, and for that purpose, we had to go about taking two models and combine them to perform this study. Getting into the problem that we are trying to solve. Right. Taking two models requires two different processes. One is the text to image, and then from image to the 3D mesh, which then again involves three different times. One is the text to image generation time, the second is the background removal time, and the third is to convert the background removed image to a 3D mesh. The average time that we benchmarked at FP32 was 13.55 seconds, which is pretty high. And hence, the purpose of our study is to reduce this time, which we successfully did by reducing it by 3 times. So how do we solve for this? Before we get into that, this is the setup that we did for our benchmarking, the architectures that we used. The two models that we used were Stable Diffusion 3 and Stable Fast 3D. Stable Diffusion 3 is a model that converts a text to image, and it's by Stability AI. We use the medium size, which has about 2 billion parameters. As for Stable Fast 3D, it's a model that converts 2D images to high-quality 3D meshes. It's based on TripOSR, which is very famously known for this particular purpose. Those QR codes are there for you to scan to learn more about these models. You can go ahead with that. So getting into the pipeline that we use to benchmark our results, the first one being we combine the two models, and on combining, we added different optimization techniques and configurations that we believe can reduce the time. We applied them individually or stacked some of them as well. After adding those optimizations, we performed a warm-up of the model and put the model to run, and finally log those results to our WANT-B dashboard, or the weights and biases dashboard. So this is the environment that we maintain for our benchmarking, which can be divided into 3 components. One's the software, hardware, and the optimization tools. For software, we use the NVIDIA NGC PyTorch container, the 24.08 version for Python 3. And as for the hardware, we used a single 40 GB A100 SXM4, where we set the clock rate to a constant of 1410 megahertz for graphics and 1210 megahertz for memory. This was along with 30 CPU cores, 525 gigs of SSD, and 205 gigs of RAM. As for the libraries and tools that we used PyTorch 2.0+, more specifically PyTorch 2.4. The diffusers library, the most stable version that's available, and Torch AO 0.4. So getting into our first optimization that we performed, that's the bfloat 16, or also known as the brain floating point format. This was developed by Google. The difference between BF16 and FP32 is that BF16 has the same dynamic range as FP32, but uses half the memory. Like the standard IEEE format is 1 unsigned bit, 8 bits for range, and 23 bits for precision. Whereas BF16 uses 1 unsigned bit, 8 for range, and 7 for precision. So that's half of the of FP32, and hence takes less time. Those are the different times that we benchmark for the different processes and the total time. The simple code change that we did was change the D type from float32 to torch.bfloat16. The next technique that we used was forward chunking. In simple words, it's basically taking your large inputs and converting into smaller chunks for so that they can be processed in parallelly more easily. This is more of a memory optimization rather than a time optimization, but it was worth studying for. As you can see, from 13.5, we went to 5.5, which is a big change. We simply enable the forward chunking for the model transformer, which is the code change that we did. The next optimization is torch.compile. Torch.compile is a very popular method and what it does is it runs the code faster by JIT compiling it into optimized kernels. So it uses techniques like dead code elimination and dead code elimination, operator fusion, and all to reduce overheads. And the main advantage of using torch.compile is it also compile graphs run more consistently and hence takes lesser time, which can be seen over there. Compared to 13.5, we have gone down to almost 4.5. That's almost around 3 times. This is the code change that we did for that. Just simply apply torch.compile. One thing to note over here is the mode that we set was max auto-tune. This particular parameter is actually to get the best kernel or the best optimized kernel for the operation that it's performing, which can be seen there. The next optimization that we did was fuse QKV projections. So this particular technique, what it does is it combines the computations for the query key and value matrices into one. So instead of performing 3 different linear transformations, it performs one transformation. And it not only reduces time, but memory as well. So in terms of time, instead of performing 3, we're performing 1 operation. And in terms of memory, instead of accessing the weights 3 times, we're accessing them once, which reduces memory as well. So this is a pretty cool method, we can say. The change for this was just enabling the fuse QKV projection for the model transformer. The next technique that we used was quantization, a pretty popular method. It's basically saying it's taking a large set of inputs and mapping it into a smaller set of output values. And these low precision numbers that are there, that it's getting converted into, use less memory and hence run a lot faster. The other point that can be noticed is integer operations are generally faster compared to floating point operations. And hence, quantization reduces the time taken. The change that we did was simply quantizing after torch.compile. And we converted into int 8 over here. So now I'll be handing it over to my co-speaker, Suvaditya, who will continue it further.
I hope you guys can hear me. Hi. Yeah, so first off, we're looking at, I'm just going to move it further ahead. Right, so what you see on the screen right now is Torch AutoQuant. AutoQuant is basically allowing the Torch kernels, while you execute it, to find the best way or the best kernel optimization that can be applied to your certain operations so that it's quantized in the best manner possible. So for example, there are 3 different kernel implementations for AutoQuant with int 8 weights. So Torch AutoQuant will basically benchmark your specific layer against all 3 different implementations and check out which would be the fastest one, and hence choose that. This applies to all the linear modules that are available in your model, and hence it'll allow you to get the best out of your architecture. How do you do that? Well, quickly just change out the quantize function and just apply Torch AutoQuant. One interesting thing to see is error on unseen. What it really does is basically ignore the different modules that are not parsed by the compiler for unseen reasons. Next, we look at sparsify. Sparsify is a pruning technique which will allow you to basically zero out certain parameters in the weights. Generally, 2:4 sparsing is considered to be a very good balance between performance and accuracy, wherein very interesting white paper from NVIDIA allowed us to understand the fact that the accuracy can be regained very quickly through retraining, even after the pruning operation has been performed, thus satisfying the fact that it's a pretty good optimization to make, given performance constraints. So keeping that in mind, Sparsify will allow you to prune and also make use of CU sparse LT functions that are available in Ampere GPUs or better. How do you do that? Well, quite quickly. You just use Sparsify, and then, oh, I'm not very sure what happened there. Oh, there we are, back again. Yeah, we basically just use Sparsify, and the dynamic quantization in place will perform the magic for you. What I want to highlight here is the total generation time. What you see on this graph is a comparison of all the different optimizations piled up on each other. So talk about BF16, forward chunking, all of them. When they're done one by one on top of each other, we see very interesting results. What you'd notice is the fact that BF16 with forward chunking and compilation, along with fusing of the QKV, is the fastest technique or the best technique for performance. We'll also see how memory plays into this entire role in the next few slides. What you see right now is the 3D generation time. Now, 3D generation time is clearly just dependent on the stable fast 3D model. Now here, you'll see that AutoQuant reduced a significant time of quantize alone. The naive quantization was not as good as AutoQuant, which is rather fairly obvious. Along with that, again, we see that compile and fuse, along with the forward chunking of BF16, is the best method to go forward. Lastly, when you look at text-to-image generation, which is the Stable Diffusion 3 medium model, we see that going from FP32, which is the highest precision available, to BF16 and its optimizations following AutoQuant, Sparsify, all of them, we see that there's almost a 4-time benefit that we gain out of all of these operations. We also see that torch.compile ends up giving pretty good performance gains over time. Now, I want to highlight here the power graphs. This graph signifies the GPU power that was being consumed at the time. If you see towards your left, you're going to see that most of the graphs, they have similar trajectories. That's mainly because of how similar the results were in terms of the memory consumption, in terms of the GPU memory consumption, that is, and also the fact that they were evenly spaced out in their own trajectories, meaning that their operations were fairly stable. You can also say the same for FP32, where their longer line is basically signifying how much extra time it's taking, how much extra inference time it's taking for each sample. Lastly, this is the GPU clock graph, which is basically telling us the fact that, of course, we set it constant. Hence, you're going to see that it's just going to be a straight line. And now, the GPU memory benchmark. If you see carefully, FP32 is way up there. And that's a fairly obvious answer because, well, it's taking more memory. But we also see that BF16 with forward chunking is the best candidate when it comes out for memory optimizations. Now, that might differ from the general consensus that, hey, if I quantize my models to, let's say, int 8 or int 4, why shouldn't it have lesser memory consumption? And that's a very fair concern. Why? Because the kernel, after quantization, did not optimize it correctly. That's our working assumption, and that was what we sort of confirmed with folks over at the compiler teams. And that's what we understand, that as it stands, quantization with all of the different optimizations piled up together is very difficult to get in terms of the optimization of the specific Triton kernel being generated after the compilation process. So just want to show you some samples that we generated out of this process. So what you see on here is a throne. This was generated using the process that we described, where the prompt was basically a throne covered in pure gold, detailed 8K, right? So we could see something generated. Following that, if I just move on further, oh, this is the other. Same one? Oh, OK, yeah, there we go. So we also generated a unicorn. I mean, that's sort of different. You have the detailed colors and its rendering quality. Following that, we also generate a very specific creature that is obviously mythical in nature. A dog with the head of a lion, that was the prompt we gave it, because we wanted to see how much creativity it can render with, and it was fairly OK. I cannot say that it was great, but it was fairly OK. And I mean, there's some bloopers as well. So we didn't get, obviously, everything right. It's not great, right? It can't handle everything. So yeah, I mean, we tried the prompt aircraft with the name PyTorch Airlines on top of it, and well, that's what you see up there. So what are the learnings here? First off, the fact that naively piling optimizations on top of each other really does not work. If you keep putting one optimization on top of another, there may be edge cases where combining these optimizations may end up to erroneous results or erroneous bugs that may be edge cases for the compilers. Secondly, the only way to learn what combination actually works is very much just experiment, experiment, and experiment. Third, converting from FP32 to BF16 is a very quick and surefire way to get some very good performance boosts right off the bat. But another cause for concern is the fact that most models, as of today, are not very numerically stable. So before using this technique, please make sure that your model is stable enough to handle quantization. Also, understand the fact that diffusers, specifically, uses scale dot product attention or flash attention, as most of folks would know, if your PyTorch version is greater than 2.0. Lastly, using AutoQuant is another very quick way to just get performance boosts instead of just doing naive quantization. Just calling one specific function will allow you to optimize the kernels you're using. Right. A quick acknowledgements. We got a ton of help from Sayok Paul from the diffusers team at Hugging Face, as well as Aritra Roy Gostipati from PyImageSearch for this presentation. Robert Brooks, the fourth, helped us with GPUs for our experiments, and Soumik Rakshit from the weights and biases team helped us for the visualizations. Lastly, Horace Hay from the PyTorch compiler team helped us out in debugging the unknown. So please feel free to check out the resources. We have open sourced the WANTB dashboard. We have open sourced our code, as well as all our results on there. Please feel free to use that QR code. Yeah, lastly, that's us. We are students at USC, the University of Southern California. We are research assistants at the Institute of Creative Technologies and ISI, Information Sciences Institute, respectively. Also, we are looking for summer internships, so if you feel you're up there, please, let's chat. Right, thank you. Have a great day.